microRNA biogenesis, right? The creation of microRNA. And in this pathway, there's this thing called drosha. It's an enzyme that cuts off the arms of the microRNA so it can be processed and turned into microRNA, right? So another thing that I'm looking at is this part, this protein called Argonaute 2. So Argonaute 2 is part of a complex that essentially kind of helps stop messenger RNAs from producing certain proteins, right? So yeah, Argonaute 2. Starting the increase so you have the Argonaute protein, and what drosha does is it processes microRNA it processes primary microRNAs turn into actual microRNAs, probably steps in the pathway, and then it's loaded onto these proteins of Argonaute. And once it's loaded, what Argonaute does is it helps to either bind it to a messenger RNA, it helps it find its target messenger RNA so that it can control the gene expression of that messenger RNA, right? So what I wanted to do was look at a drosha knockout cell line, which is where we can completely get rid of drosha in the cell line, and I wanted to compare that to a wild type of the same cell line. This is actually a colon cancer cell line, taken from an adult male that pretty much I in my lab, right? But I wanted to kind of answer the question is that if we get rid of drosha, we don't have microRNAs anymore, right? So what happens if I don't have microRNAs in the cell? And from that, how is that going to affect where I can find the Argonaute protein located in the cell, right? So one of the first things we do is actually really important for this process is a chromatin fractionation, which is a protocol that my lab specifically has optimized so that we can have as pure of a chromatin sample as possible, right? And this is important because chromosomal DNA is what actually makes RNA, right? So theoretically, right, logically, if I look at the RNA in the chromosome, I'll have I can directly look at kind of the scene of the crime, right? And so I have specific information on how RNA is formed, what's happening, right? So I do a BCA protein assay, find how much protein is present in the sample, so that I know how much to load onto my Western blot. Western blot is more or less then to figure out if I have a protein in a sample, and if I do have a protein, how much of the protein do I have in the sample, right? So in my results, you can see here I have my wild type, which is just the normal cell, natural conditions, and then I have the drosha knockout cell, which is getting rid of this thing over here, what makes microRNAs. So these three are the controls that we do to make sure our methods are correct, and that what we're doing is actually accurate, so I can trust my results, right? So in the wild type, you can see that Argonaute shows up not only in the cytoplasm, where we would expect it to show up, but also in the nucleoplasm and the chromatin. So this is actually mind-blowing because this means that potentially Argonaute is involved in processes like gene silencing, in gene splicing, and gene transcription, which honestly completely changes how we look at disease treatment, because now we have this whole new set of targets that we can use, a whole new set of targets that we can use to either modify or silence them to treat certain diseases that have targets that we might not have known about before. So in the drosha knockout cell line, you can see that again we do have controls to make sure the methods are correct. But even though it is a little bit more abundant in the cytoplasm, Argonaute still shows up in the nucleoplasm of the chromatin, right? So this is actually not, this shouldn't technically be happening, right? Because we got rid of the microRNA, and microRNA being loaded onto the Argonaute protein is what allows it to shift on mutations, right? So theoretically, if I'm getting rid of the microRNA by getting rid of drosha, I shouldn't see it anywhere. However, because I do see it, potentially what could be happening is Argonaute is just a protein that wants to bind to an RNA, right? There could potentially be microRNAs that are independent of drosha that are still somehow being loaded onto the Argonaute protein, so it can shift these messages. Or another thing that can happen is that it's just binding to some kind of RNA that's not necessarily a microRNA, and that RNA is still allowing it to shift into the nucleus. I'm not entirely sure the role of Argonaut when that happens. Yeah, usually Argonaut is just helping microRNA find mRNA targets. So not that messenger RNA won't be able to code for proteins.
So what determines the localization of Argonaut?
So my lab is actually what found, like the lab that found that this protein can be found, or this protein and also microRNAs that are involved in this process can be found in the nucleus, right? So the process that happens is that through structure we're cutting off a bit of the microRNA, the arms of the microRNA, so that the microRNA can kind of fully be processed and be sent out into the cytoplasm. And the cytoplasm is being loaded onto the Argonaut protein. And once it's being loaded onto the protein, the microRNA is what allows the protein to shift into the nucleus. Right? So here it's expected, well, after like previous experiments, it makes sense now that it shows up in the nucleus because it was loaded with the microRNA.